here. So this lecture is lecture 4 part is this lecture basically discuss the documents that you're going to be generating for your project. It's the title of the lecture is Systems Engineering Documents. And so again, as you saw in the description of the project, you have to generate, I think, about 8 documents for your project. Those are engineering documents for systems engineering. You're gonna find in your professional career, if you go through this field, that there are multiple ways of writing a report for a systems within the system engineering field. But in this lecture, we're gonna cover the ones that I'm expecting you to complete as part of your project. And these are this is material that is covered in part on your book and also on this reference site of the University of Arizona. Okay, so before we get into the system documents for the project, we are going to talk also about the systems engineering as part of the project management and also elements of a typical systems engineering management plan. As you can see in this slide, there's the 8 documents that I was referring to. At this point, I think we have covered half of the explanation for them. We get to the other part that's not necessarily on the need analysis phase. The second part of the documents, those concept exploration, use case model, design model, and mapping and management are more into the concept development phase, and we're going to talk about that also during the rest of the semester. But before we get into the documents, systems engineering is part of the project management. Project management's principal constituents are systems engineering and project planning and control. So I think you're in manufacturing. So for IE students, we have a course specifically on project management, which now is becoming part of the capstone design, the 2-semester capstone design. So in that course, basically we teach the project management skills in terms of planning activities and writing a statement of work, and so on. So within the project management's principal constituents, we have the project planning and control and also systems engineering. The domain of the systems engineer is technical guidance of the entire project. So again, we're focusing on the engineering portion or the engineering component of the development. Project planning and control focus on financial and contract guidance. So are we meeting the deadlines? Are we meeting the budget that we have available, the resources that we have available? So in this figure, you see that there's overlapping between the two in terms of defining the task and also the risk involved and also having interaction with the customer. So proposal development, and we've been chatting a little bit about this already. System development often starts with someone who has a need, which is what we're going to call the customer, who requests support in the form of a request for proposal. So, so this can be seen in multiple areas: healthcare, energy, the Department of Defense. They are always putting out proposals for universities or companies to address some of the issues that they cannot manage with the resources that they have available. So those announcements are in terms of so we need to develop a new machine, or we need to develop some new algorithms to help us make decisions, and so on. Within each company, you can also see those type of problems. So your boss can come up to you and say, okay, we have these problems. I want to generate a solution for this. This is also seen a lot within the research and development within companies, like, for example, Apple or Samsung, that they will subcontract companies to address some of the issues that they have in their products. So often you start with someone that has a need. That will be the customer, and that's this person or this group is asking for support in terms of a request for a proposal. And then once that's out of there, people can submit their proposals with their methodology to address that problem. And then usually one of them gets picked based on the proposal. A program manager or professional team is assigned to generate the proposal. And the integration of systems engineering with project managers is evident in the early phases of the project, since it is essential that the technical concepts and implied design and interfaces are feasible. So if you are awarded the proposal, then we had to come up with an integration plan and see if that the ideas that you're proposing are actually technical and also implementable. Statement of work. So as I mentioned, that's one of the things that we discussed in the project management class. This is a critical element of the proposal, is the statement of work. It's the narrative description of the work that is needed to develop the system to meet the customer needs. So this is what we're going to do. This is a narrative of what we're going to do to meet the expectations for the system. The systems engineer concerns focus on the product and services needed to complete the effort. So are they responsive to the customer needs? Are these statements or requirements that we are listing actually representing the customer needs? Systems engineers will ensure that the statement of work is based on a credible concept of operations. So it is technical, feasible, it's something that we can generate. Reviews the implied design for the use of legacy components and their availability. So in terms of legacy components means that can we use some existing technology to come up with some of the parts or subsystems of the system. Examines to see if the proposed system concept integrates commercial off-the-shelf components. Again, are they available, something that we can purchase, or determines the technology readiness level for the importance of system ambitions in the preliminary design. Sometimes we are proposing things that require some new development, so that's what this is referring to. So some of the things will be ready, some of the things might not be ready. So if it is feasible for us to come up with those components that are not necessarily ready in terms of technology. Another document or diagram, sometimes it's represented as a diagram, is called the work breakdown structure. This is used to basically delimit all the activities that are going to be part of the design and implementation of the system. So the successful management of the system development effort requires special techniques to ensure that all essential tasks are properly defined, assigned, scheduled, and controlled. One such important technique is the systematic organization of the project task into a hierarchical structure called the work breakdown structure, or WBS. With the system project at level 1, that will be our goal, right? That's what we want to achieve. The level 2 items can be given as follows. 1.1, that could be one of the sub or the next level in this breakdown. System product, which is the total effort required to develop the system. 1.2 could be system support, which are the integrated logistics supports. System testing, something that we have mentioned over and over again. It's not just designing the product, also we have to provide for testing to minimize the risk of implementing the system. So system testing includes all the testings after component validation. And then 1.4 is project management, which includes all the activities related to project planning and control. And 1.5, systems engineering, which focus on the system development activities identified in the Systems Engineering Management Plan, or SEMP. Okay, so a word breakdown structure again, allowing us to see the hierarchical structure of all the things that might be needed to complete our system. So here's a representation of what we are trying to achieve. Again, this is just for the system product. So at the top level, we have the system product, then system 1.2, or that should be the overall system right here. And then 1.1 is basically representing this next level. And within within that level, then we have multiple subsystems, multiple components that are part of each one of the subsystems. And then at this level 5, we are basically listing the activities that are going to be part of each one of those components. System support, that's 1.2. The goal is to provide equipment, facilities, and other support for the development of the system. So that involves supply support, test equipment, transport and handling, documentation, facilities, personnel, and training. So everything that goes around the actual system, supply meaning that are we able to supply the input required for the system to function, test equipment, if we are going to perform an evaluation of some of the outputs, do we have the test equipment available to perform those tests? Transport and handling, this is something that we can move easily. Do we need a crane, or do we need a truck or special material handling equipment to move the system? Documentation, this could be like we find for software development. Like if you don't know what instruction is doing, you can search and see the documentation to tell you what it's supposed to do. Also, if you buy a new car, you see that it comes with a book. So that's what this is representing, the documentation. Facilities is the system needing to integrate with other facilities outside the manufacturing process or the production process. Like a car, it will need to go to a gas station, or it will have to go to a mechanic. Do we have those facilities in place? Personnel training, that's self-explanatory. So the people who are going to be using this or interacting with the system, are they properly trained? Do they need to go through special training? System testing, the testing of the operation and the integration of the different components of the system. Individual testing of components has usually been completed, and most overall testing effort is spent in this stage. Some of the categories of tests: integration testing, support the stepwise integration of the system components. So when they put together, are they performing as expected as a subsystem? System testing provides overall system tests. So if at some point it's not working properly, can we diagnose and see where is the problem? Acceptance testing provides for factory and installation tests of delivery systems. So once you have moved that to the actual customer, do we have a benchmark, or do we have some parameters that the system has to meet when installed to say that it's working at an acceptable level? And operational testing tests the effectiveness of the system in a realistic environment.
So this testing is referring to like simulation testing or prototype testing specifically, or is it like testing throughout the entire life cycle?
That's a good question. And the question is if this testing involves simulation modeling, and if this happening only at the end phase of or implementable phase of the system development, or is this something that is happening throughout the whole process? Well, that could be answered. It's a mix. Like throughout the process of developing the system, you're gonna need to develop some new components that are going to be part of it, right? So yes, so when you develop those new components, those that are new in the sense of not being used before, then you have to perform the test for that specific components to make sure that it's performing as expected. Even though that you had not finished the actual completion of the system, if you are developing something new, the testing has to be performed for anything that you are developing as new in the sense of not being available before or not being put into production or not being used in any other system before. Now, when you get to the overall system performance, like now you have the whole system together, you also have to perform some additional testing to make sure that this new system that might be new only because you have that new component, right? Like in the case that we discussed for the engines, like gas engine and hybrid engine is the same car. The only difference is the engine. So now you have to perform new tests at that level, like when you have the whole system together to make sure that the whole system is performing as expected. So yes, so you perform tests, anything that is developed new that is going to be part of the system, the integration of those new components, and then at the end when you have the whole system now ready to be tested in the environment where it's going to be operating. And I think that those four bullets are summarizing each aspect of this process. Um, Operational testing, acceptance testing, system testing, and this is not only, and you can use simulation, like at the level in which you're not necessarily having the system together, like you are just in the level of prototyping or again, if you're developing something new, you can use simulation to see if I use this design, how it will perform, and then I can use that simulation to test how implementing this new component will affect the overall system. So simulation is one strategy for sure that you want to consider. But when you get onto the actual system, now you have a better understanding of how it's supposed to behave because of the simulation results. The other part about the testing is that you have to make sure that you have designed for testing ports that would allow you to perform those tests. Like I always go back to the car example because you're familiar with it. So in the cars, if you go to the engine or if you go into the interior cabin, the car will have some ports that you can use to put machines and do the testing of the car and make sure to identify where the problem is. So that's also part of our design in terms of the testing. And then 1.4 project management. These are all the activities associated with project planning and control, including the management of the work breakdown structure, or WBS, that's cost, scheduling, performance measure, and project reviews and reports. Project management has cost control and estimating. Need to focus attention on components which deviate seriously from the initial cost estimates. So as when you start a new development and you're planning for your budget, you are always recommended to have some extra amount being added to that project development in case something doesn't go as expected. So that's when you try to manage that uncertainty. If you're part of the development or the construction of a new building, you know that there are things that can happen that are out of your control, like weather conditions and so on. So when you're planning for those major developments, cost control and estimation has to be very aware of those risks, that uncertainty for planning for your cost. So need to focus attention on components which deviate seriously from initial cost estimates. So as the example that we covered for the hover, that they needed to develop these new lenses, and they didn't plan for the testing. They didn't account for that extra money that will be needed for the testing. So at that point, again, you've submitted a proposal. You got a proposal accepted. You only have so much money to be used to develop that. So you have to pay attention. If it's really worth it, can you switch some of these cost estimates and that allocate that money from another part of your budget to make sure that you have the right design? So cost control and estimation is very important. The critical path method. Are you familiar with the critical path method? Basically, it's a network scheduling technique that allow you to trace the major elements of the system through the engineering critical path. So you have all the activities, you have the lead times, you have the production time that it's going to take you to complete each one of these activities, and based on that, you can trace back the longest time that you will need to complete the project. Estimates are made of not only the size but also the duration and effort required for each step. The particular path that is estimated to take the longest time to complete its activities, that's what we call the critical path. And then systems engineering includes the activities of the system engineering staff in guiding the project through all its major phases, such as requirement analysis, trade-off studies or analysis of alternatives, technical reviews, test requirements and evaluations, system design requirements, configuration management. These activities are all part of the SMP. This is the SEMP in program management plan. I'm just showing you this for reference purposes. We don't necessarily have to go in depth in terms of, but that's this is where it stands, and you have the program technical requirements, the program management requirements, and also the program management plan, which starts with the program requirements, all of them connecting to this systems engineering management plan. And then you have the responsibilities for these three listed below each one of these three areas. Okay, so the second part of this lecture is to discuss the systems engineering documents for the course project. As you know, you have a project, a semester project that in which you have to develop a new system that is an engineering system that is trying to solve a problem that has some societal need. Okay, so these are the 8 documents that you have to prepare as part of your final report. The first one is the problem situation. Second one, customer requirements. Third one, detail requirements or detail requirements. Number 4, system validation. Number 5, concept exploration. 6, use case model. 7, design model. And finally, 8, mappings and management. So at this point in the semester, you can start working with the first 3 documents, problem situation, problem, customer requirements, and detail requirements. Problem situation, you have already described that as part of your proposal, so you can use that and refine that as part of the project. Customer requirements and detail requirements, we have a good discussion on those in the last 2 lectures. We describe what are the type of requirements. We have 6. Those are relevant. You need to know them. Not only for the project, but also for the exam. You need to know what are the 6 different type of requirements. And what they mean in terms of what they're looking for. And On Monday, we also discussed how to write the requirements. And we're going to touch on that also today. So there are certain strategies that you need to follow in order to write the requirements for your project and for any other system that you are going to develop in the future. So in terms of project assessment and in terms of your next report, which is the progress report and also the project report, you have to write the requirement in the way that we discussed on Monday. So if you were not here, I encourage you to look at the video, which is already posted on Tracks. So we are going to touch on that today, but the discussion, the general discussion was took place on Monday. So problem situation, as I mentioned, you already talk about this in your, or you discuss this, or you write about this in your project proposal. It's an executive summary, basically discusses the problem situation, state the problem, describe the customer and its stakeholders who care about this problem, who is involved in this problem. And in the final version of this, it describes the preferred alternative. So again, an executive summary in the sense of not only describing the problem, not only describing the stakeholders, but now that you have gone through the process of developing something to solve this problem, what was the recommended alternative for you? You have to describe that alternative also as part of the problem situation, this executive summary. Also highlights the performance, cost, and schedule and risk for the system that you're proposing, that new system. This is intended for management and the public. So you don't want to go very technical. You can explain your solution in terms of why is it better, maybe in terms of cost, in terms of performance, in terms of risk. You can touch on those. And again, making sure that it's intended for management and the public. In terms of problem situation, complete the problem statement before defining the requirements. That's very important. You need to understand the problem very well in terms before you want to state the requirement. Why is that relevant? Well, if you don't understand the problem, then the requirements that you are going to list might not address the problem that you're trying to solve. So remember that you will not focus on the symptoms, right? You want to look at the symptoms are, okay, I have a fever. The solution is, well, what is causing that fever? So that's what you want to identify. What is the problem? Avoid stating the problem in terms of solutions. Involve the customer in the process of defining the problem and the requirements. This is the foundation for a successful project. In your project, you are both. You're the customer and also you are the developer. So that will be kind of difficult to realize in terms of your project. But if you want to get a little bit detail in terms of defining the problem, maybe you can discuss with me and I can certainly push a little bit more in terms of as a customer perspective. Early in the system design, consult all stakeholders, including manufacturing, reliability, availability, and maintainability, about the system requirements. Stakeholders are the people who are going to benefit from the system to be designed or those who will be affected by it. Okay, so start building while you're still designing. Meaning that you are building on your project. This is an iterative process, right? So you are, as you gather more information, as you see how things are fitting in the development, you can always come back and refine your problem situation. Customer requirements. This is detailed problem statement based on the specific requirements sections of the use case. We're going to talk about the use case later this semester. But recall that writing the requirements, you have to follow these three, or you have to use one of these three words in each one of the requirements that you're going to state. So shall requirements, you shall to write a requirement that is contractually binding, must be implemented, and its implementation is verified. Will are facts or declaration of purpose. Use will to indicate statement of fact, but this will not be subject to verification. For instance, the system will be replaced after 3 years. That's a statement, but that's not necessarily something that you are going to verify at the end of the design. Should goals non-mandatory, or the use of should, goals non-mandatory provisions use should to indicate a goal which must be addressed by the design, but is not formally verified. So for example, the spacesuit should not impede the crew mobility. This is intended for management, the customer, and the systems engineering. Detail requirements. These are the technical description of the problem statement, system design requirements, trade-off, test plan, also the verification matrix. How are you going to verify your requirements that they are satisfied? This is intended for engineering. And we talk about the different type of requirements, as I mentioned. So input, output, performance requirements, cost requirements, trade-off requirements. Those are the ones that you have to list in the derived requirements document. Okay, so those are the requirements that I'm expecting you to discuss in this document. System validation shows that the system and the set of requirements satisfy the actual customer needs, checks the requirements for consistency and completeness, shows that a system model can satisfy the requirements, ensures that a real-world solution can be built and tested to prove it satisfies the requirements. So recall in our discussion the difference between these three systems: functional system design, buildable system design, implementation system design. So how do you ensure that you go from a functional, or that you have a functional, that you have a buildable, and that you have an implementation system design? Those are the things that you have to discuss here. Recall that validating system requirements means ensuring that the set of requirements is complete and consistent. A real-world solution can be built that satisfies the requirements, and it can be proven that a real-world system satisfies the requirements. If the requirements specify a perpetual motion machine, the project should be stopped. That's something that you cannot do, right? So each requirement must be verified by logical argument, inspection, modeling, simulation, analysis, testing, or some type of demonstration. Okay, so we talk about problems, we talk about the requirements, we talk about how are we going to check that the system is validated. Then we move to the concept exploration. Investigate alternative designs, alternatives A, B, or, and do nothing. The do nothing alternative always have to be listed. Okay, because it's maybe doing nothing or keeping what you have is the best alternative. The alternatives shall use new unproven technology, produce incipient initial architecture. So this is how the system will look like. Use evaluation criteria in trade-off study. So we talk about this also on our previous lecture. What are the performance figures of merit, the cost figures of merit, trade-off figures of merit, and also the risk. And this is due in terms of unproven technology. Present sensitivity analysis. Explain the do nothing alternative. Again, this is an alternative that we have to list and discuss. Should be readable by the public. And then we have the use case model. We're going to spend more time on this later this semester, maybe towards the end of the semester. A use case describes a function the system shall perform. Okay, perform functional. It is used to perform functional decomposition. A function, or a better phrase, is a process that transforms an input into an output. Okay, so decompose the top level system function into sub-functions, sub-functions, and so on. This is intended for management engineer, the customer, the public, and the systems engineering. Use case model are used to discover functions the system must perform, list an input that will be transformed into an output by that function. For example, suppose your customer has a box of papers she wants to get rid of. So at the high level, you have an input, which is the box of paper. The function will be to get rid of the paper, and the output will be an empty box. Right? So the low level input will be the paper, the function. How are you going to get rid of the papers? You can use, you can burn the paper. What will be the output of that function? The ash. Okay, so we start decomposing. What do you want to achieve? Okay, so what are the low-level things that are part of this input? Well, the paper. How are you going to get rid of the paper? Well, in this, you have multiple options. It could be one, burning the paper. You can recycle the paper. So what will be the output of recycling the paper? All those things. So this is a slide that is used to show you the difference between what we call physical decomposition and functional decomposition. So for a long period of time, people try to unsuccessfully to fly. And the reason for that was that the designs that they were coming or trying to come up with were focused on physical decomposition, meaning that they were trying to replicate, like the birds have wings, so maybe for us to fly we need to develop some type of wings and use those wings to try to fly. That's what we call physical decomposition. However, if we look at the problem from a different perspective, in this case functional decomposition, what the Wright brothers were able to do was to focus on the three functions that are needed to fly: control, horizontal thrust, and vertical lift. And by mastering those three functions and making sure that they work together, they were able to develop a machine that was capable of flying. Okay, so by looking at the problem from a functional perspective, what do you need to do? What do you need to do in terms of functions to make sure that you can elevate and fly? Well, that they were able to split those in three functions, and they find out a way to balance those three functions to make that happen. So that's one of the things that we are trying to achieve with the development of this use case model. We understand the functions that are available that can be used to achieve the goal of the system. So we are going to use use cases to perform those activities. Use cases should be named with verb phrases given in the active present tense form from the point of view of the system or the primary actor. If you are using the viewpoint of the primary actor, the name should reflect the goal of the actor. Use case name should not relate to any particular solution. The verb should be in imperative mood. Use case names are usually written with the first letter of each word capitalized and space between the words. It is helpful to set up use case names in a different font. So this is what I'm referring to in terms of a use case model. And I'm going to teach you how to build these diagrams later on. So the idea of a use case model is to list the functions that are part of your system, and then also show how the actors, which are the entities interacting with your system, are going to be interacting with those functions. So the functions are listed in those circles or that are here. This is for HVAC system, so each one of them will represent a function of the HVAC system. Heat the house, set temperature limits, cool the house, select equipment, and display the system status. And then using those functions, or after we identify those functions, then we can see, okay, who's going to be interacting with these functions. The homeowner, maybe he's going to be interacting with each one of the functions. The heater, that will be the equipment or the actual heater system. So How is the heater system interacting with the functions? How is the AC interacting with the functions? So that's the idea of these use cases. So if you can split the functions of the system, you can see how the actors or the entities that are going to be using the system will interact with these functions. And again, this is intended for management, engineering, the customer, the public, and so on. Design model, we're going to skip this for now. We're going to talk about this later. And then finally, we have the mapping and management, which we can discuss later on when we are more into the project. So we will go back to this later on. So this is a summary of what we discussed today in this lecture. I encourage you to go through these lecture slides again, over and over again throughout the semester, so you have an idea, especially when you're working on your project, that you are doing what is supposed to do for each one of the documents. And this is what you're going to report at the end of the semester for your project. Any questions